All right, let's go ahead and get started. I don't think there are all that many administrative things to announce. There has been a revision to Homework 1 that was only there to sort of clarify the instructions for, what is the protocol for actually submitting things given there's group homework assignments. And what do we actually want you to write down when we ask you for a dynamic programming algorithm? So there's a bulleted list on the front. There may be, it's been suggested that perhaps one of the sentences in one of the problems I could write in a clearer way, and I'll try to do that soon. Delta is the cost of a delimiter, not the number of delimiters in problem 1. Otherwise, I don't think there's anything that I need to announce in terms of administration. But if anyone has any questions, now would be a good time to ask. Okay. So now we're starting to get into somewhat more interesting dynamic programming material, because so far we've been mostly concentrating on the first 4 steps of the pipeline. So if you remember, the standard set of instructions for building dynamic programming algorithms is first you come up with a recurrence, and second you figure out how to memoize it, meaning you need a data structure. You need to know what the subproblems are that you're going to memoize. Third, you need to basically figure out an evaluation order so that you're filling the memoization structure on purpose. And fourth, you do the analysis. And for this class, that's always going to mean time analysis. But then there was this 5th step, where you optimize. And so what I want to show you over the next the next 2 lectures is a few interesting non-trivial ways to optimize dynamic programming algorithms. None of these is obvious. None of these are things that really most people can expect to just have in their arsenal. Right? They're very useful to know if your performance really depends on getting your dynamic programming algorithm to be fast or to save space. But these are not standard tools that always apply. It's more, if the problem has a particular structure, then in those cases you can apply these tricks and get better performance for your dynamic programming algorithm than what you would get by following the standard pipeline. Now, some of these optimization tricks we've already hit on, and I've said, no, hold off, don't do that. So, for example, it's often the case that there are redundant cases in the recurrence. So, for example, when we're doing edit distance, it's possible to prove that if the first 2 characters of the strings are equal, that in the optimal edit sequence, you're going to match those 2 characters. It takes a little bit of effort to prove that. It's a simple exchange argument at its core. But until you've actually done that proof, it's not really safe to apply that heuristic, because there are lots of similar sounding things that actually turn out to be wrong. This is not the kind of relatively simple thing that I'm talking about. Okay. Another one is space. For example, with Fibonacci numbers, I didn't need to keep the entire table. I only needed to keep the last 2 entries. For edit distance, I didn't need to keep the entire 2-dimensional table. I only needed to maintain 2 different rows. That's usually relatively straightforward. And this is starting to hit on the problem I alluded to earlier. You can save space if we only want the cost. Whoops. You go over there. Don't fall asleep. If you only want the cost, for example, if you only actually want the number at the bottom of the table that tells you the edit distance between two strings, you don't need to maintain the entire table. But what if we actually want the object? What if we actually want the optimal structure? All right, so for edit distance, the optimal structure is this tableau, or equivalently, the sequence of editing operations that gets us from string A to string B as quickly as possible. And it seems that if you look at, for example, here's the edit distance table again, without the arrows glued in, which are a little bit confusing. So this is the table that's actually computed if you memoize the edit distance recurrence that we've been talking about last week and earlier this week. And then the way that you might reconstruct, given that the edit distance between these two strings is a 6, the way you might actually reconstruct the optimal sequence of editing operations is to ask, well, where did this 6 come from? In this particular case, the 6 has to be either, it's the minimum of 3 things. It's either 1 plus the thing to the right, 1 plus the thing left, 1 plus the thing above, and 1 plus the thing above right. In this case, it's got to be 1 plus the thing above right. Oh, wait, where did that 5 come from? Again, I can trace this back. The 4 is red because the 2 corresponding characters are both T's, they're both equal, which means in this case, the substitution is free. It doesn't cost 1, it costs 0. So I can go back, and then I can just sort of trace out a path through the table. And then I can reason that every time I took a diagonal step, that's a replacement, which is either free or not, depending on whether it lands in a red number or a black number. Every time I go to the right, that's an insertion. And every time I go down, that's a deletion. Okay, so I can reconstruct the actual pattern of editing operations from the table. But if I'm saving space by only saving the last 2 rows of the table, I can't do this backtracking to reconstruct the structure. And so the first trick I want to show you is that you can get the best of both worlds. It's possible to have an algorithm that computes the optimal structure using only quadratic time, which is what you get by filling in the table, or even if you're saving the space, but at the same time only using linear space. Okay? So, let me actually write this down. Given the entire table, and this is not something specific to edit distance. This is actually a feature of a wide variety of dynamic programming algorithms with a memoization structures table. We can reconstruct the optimal edit sequence. Okay? So here's a fresh copy of the table that hasn't been screwed up yet. So this was an idea that is due to Daniel Hirschberg, who is currently a professor at UC Irvine, but he came up with this in the mid-1970s, when I believe when he was still a graduate student. And what Hirschberg said is, let's start just basically from scratch for the moment. I have these 2 strings, altruistic and algorithm. Okay, I need to transform one of them into the other. And if I think like somebody who's doing dynamic programming, the question that I'm going to ask is, what do I do on the far left, or what do I do on the far right? And what Hirschberg said is, let's actually change the question slightly. So instead of just chewing things from one end or the other, let's just jump straight into the middle. Okay? At some point, I'm going to align some prefix of the word algorithm with the first half of the word altruistic. And I'm going to align the remaining suffix of algorithm with the corresponding suffix istic. Okay? So I'm going to split the first string altruistic in half into two smaller strings, altru and istic. Now when I align the two big strings, some part of algorithm is going to be aligned with altru, and some part of algorithm is going to be aligned with istic. And I don't know where that split is going to be. I mean, in fact, the split that's suggested by just drawing the line straight down is not terribly bad, but it may be that the optimal way of splitting it is to match altru with algo and to match istic with rhythm. So the alignment might look like, well, that didn't work. Again, the proper alignment might. Come on, you can get it. You can get it. There we go. Thank you. Okay. The proper way to split up the problem might be, let's take the first half of string A and align it and edit it into the first 4 characters of B, and let's take the second half of A and edit it into all but the first 4 characters of B. The question is, where do you split? Okay, so which prefix of B aligns with the first half of A? Okay, now I don't know the answer, of course. Assuming string B is n characters long, I have n plus 1 possibilities for the answer to this question. It could be that all of B matches with the second half of A. It could be all of B matches with the first half of A, or it could be anything in between. So I need to decide some number between 0 and n characters to go at the beginning, and n minus that number to go at the end. And once I've figured out the answer to this question, I can now pass off the problem to the recursion fairy. Because now I said the recursion fairy, you figure out the edit distance between altru and algo, and then you figure out the edit distance between istic and rhythm, and then I'll just add those two numbers together and I have the edit distance between the two strings, assuming I got the split right. But more interestingly, you figure out the optimal edit sequence, the actual structure that matches altru and algo, and then you figure out recursively the optimal sequence structure for istic and rhythm, and then I get the optimal sequence for the whole string by just gluing those two structures together, assuming I got the initial split correctly. Okay? So how might I figure this out? So there are a couple of different ways to do this. The one that Hirschberg actually came up with, which is the one that's not in the notes, relies on the fact that the edit distance between A and B is the same as the edit distance between the reversal of A and the reversal of B. I can think about prefixes essentially by going, thinking about edit distance in one direction, and I can think about suffixes by thinking about edit distance in the other direction. So this is the information that I would, if I could compute the following information, I would be done. Okay? What I want is So I'm going to just name the functions. Prefix left of I, this is the edit distance between the left half of A and the prefix from 1 to I of B. Okay? This tells me for a given choice of algo or alg or algory, what its edit distance is with altrue. Okay? And then the second thing I need, not surprisingly, suffix right. This is the edit distance between the second half of A and the suffix of B. Let's say the suffix of B starting at character I. Okay? I'm sorry? They both contain I. This is an argument to a function. This I is scoped within this definition. This I is scoped within that definition. I have two functions, each of which has a local variable called I. They're different. Okay? All right, so suppose for the moment I actually had these values. Let me move this out of the way for a second. First, suppose I actually knew these values. Forget for the moment how we would calculate them. What is the edit distance between all of A and all of B? Yes? Or I could pass in I plus 1 here. I remember, this is a local variable. I'm going to keep the notation in the code simple, but I can pass in more complicated arguments. Okay? Remember, this I isn't a number. It's a local variable to this procedure that the specification that I've written. There is no I until I call this function, and then I is whatever I pass into this function. Okay, so what is edit of AB? So this is the minimum. The minimum over all I of pref left of I plus suff right of I plus 1. Okay, so once I have these two, once I compute all possible values of these two functions, then in linear time, by doing a for loop over the values of I can figure out what the edit distance is between A and B. Moreover, if I actually had the optimal structure, if instead of edit didn't just return the number, but it actually returned the sequence of editing operations to go from the left half of A to this prefix of B, and suff right actually gave me the list of editing operations to go from the right half of A to the suffix of B, then to get the optimal sequence of editing operations to go from A to B, I would just concatenate the optimal sequence for the left part to the optimal sequence for the right part. Okay? So if I can compute those structures quickly, then I'm done. Okay. How do I compute pref left for all I? First of all, before we get to how to do it, is everybody clear on why the two things in red give you the thing in purple in linear time? Yes?
Would you always use m over 2?
You don't, that's actually not that. The question was, would I always use m over 2? That's not really necessary. In order to get, eventually when I get to the analysis, what matters is that there's a constant factor decrease in the size of the subproblem. Eventually, what I'm really doing here is a divide and conquer algorithm. And ultimately, the analysis is going to boil down to a descending geometric series. So as long as the sizes of the subproblems decrease geometrically, it doesn't have to be exactly half. It also doesn't have to be A that I split in half. I could split B in half if that would make things better. Yes?
Could this still be valid at the point of where we divided the B string in the optimal alignment we have insertions and divisions?
Well, so if you remember, I had this, the way that I'm thinking of the alignment is I write the two strings with gaps. And essentially what I'm asking is, if I write the two strings with gaps that represent the optimal alignment, and then I draw a vertical line that splits A in half, how did I split B? And that's going to be, the left half of that optimal alignment is going to be the optimal alignment for the left halves of the strings. And the right half is going to be the optimal alignment for the right halves of the strings. Okay. How do I compute pref left for all I?
Is it possible to do a binary search?
It's an edit distance function, right? Remember how the edit distance recurrence works, right? This is the edit distance between A from 1 to I and B from 1 to J. That's the specific, this is notation, right? So edit ij, this recurrence that we've already figured out how to solve, if I plug in different values of I and j, I'm going to get the edit distance between different prefixes of A and different prefixes of B. Okay? So, and the memoization table actually computes the edit distance between every prefix of A and every prefix of B. So, how do I compute these particular edit distances between particular prefixes of A and all prefixes of B? I run the algorithm I already saw, right? These preferences are here. I look at the row of the table corresponding to the prefix ALTRU, and every entry in here is the edit distance between ALTRU and some prefix of algorithm. And I know that I can actually compute this row that I've highlighted in quadratic time, because it's almost half the table, and only linear space, because I only need to keep two rows if I'm only interested in the values. Okay, so we already know how to compute all of these values in mn time, and I think, yes, m is the number of rows here, so this is order n space. Because this is just a standard edit distance calculation. We already figured out how to do that. So that's how you compute edit distances between prefixes. How do you compute edit distances between suffixes? You look in a mirror, you stand on your head, you run the you can change the recurrence so that you go from the left instead of from the right. You can reverse the strings and call the standard edit distance algorithm. But again, it's going to boil down to computing a particular row in this dynamic, in the corresponding dynamic programming matrix, except I've reversed the strings. I'm sorry, I don't have that example at hand. Okay. All right. So I can actually compute both of these things in quadratic time and linear space. And then with just order n more time, I can figure out how to glue the two parts together. But more importantly, in order n time, I can figure out what the right value of I is, where I should split B into the left half and the right half. And what this is going to correspond to in this dynamic programming matrix is nailing down one cell of the matrix. This is the place where I should split B into the left half versus the right half. Or another way of saying this is I have now learned that the optimum path through the dynamic programming table goes through this cell. Once I've learned that, I can now do the following. I can say, well, I've just learned that there is an optimal alignment that sends algo to altrue. And there's and the same optimal alignment sends istic to rhythm. And so none of this stuff matters. And now all I'm going to remember is this 3 here. Actually, I don't even need to remember the 3. I don't even need to remember the values. I'm just going to remember, I'm going to put my finger here. And now, again, I can say, oh, now that I know how the right split is, I can compute the structure up here, I can compute the structure down there, and just glue them together. How do I do that? I recurse. I don't do it. I let the recursion fairy do it. Right? And now, the interesting thing is, all that we have left to do is the analysis. Right? So, what we did, the whole point of this exercise, is to go back and say, well, okay, here is if we had the full table, we could trace back the path from the bottom left to the lower right. All I'm asking is, where does that path intersect the middle row? And now I can recurse on, the upper left part of the matrix and the lower right part of the matrix, and glue the two recursive structures together and get the structure I want. Okay. And to get to this point, to know that I should, this is the pivot where the optimal path crosses through the middle row, I've used quadratic time and linear space. Okay.
Shouldn't you keep the row and column that the pivot are in?
I'm sorry?
Shouldn't you keep the row and column that the pivot are in?
Yeah, well, I know that the row is m over 2. So the information that I've actually computed is the column, the position of this box.
But I mean, when you recurse again, you should do it on the string, including the pivot, or?
So there's some boundary issues here about whether you want to include the pivot in both subproblems or only in the left subproblem, and that depends on the particular way that you phrased the recurrence. I believe the way that I've set it up here, you want to include that pivot element on the left subproblem, but not on the right, which is the picture that I drew here. Okay? All right. So if I recursively compute the optimum edit sequence between altrue and algo, and I recursively compute the optimal edit sequence between istic and rhythm, and glue those things together, then I'm done. So how much time does that actually take? Well, I'm going to write down a recurrence. And the recurrence is going to have 2 arguments because I have 2 strings of 2 different lengths. Yes, there's a question in the back.
What is the direction of the highlighting the feature?
That's a big gray box.
I'm saying on the previous one, when you were describing the time.
Oh, so when I did this reconstruction, I said, first let's fill up the numbers, and then from here I'm going to walk my way back up to to the 0.
Yeah, but what does the up and down versus the diagonal do? What does that mean?
So I believe if I've got the correspondence correctly, if starting at the top and going down, if I go diagonally, that's a replacement. If I go horizontally, that's an insertion, and if I go vertically, that's a deletion. Yes?
How do you know that the optimal one's going to be split somewhere even?
It's got to go through the middle row. I'm not claiming that this thing is going to be in the middle of the row. All I'm going to claim is that it's the middle row. And that's going to turn out to be enough. Yeah?
What do you do for the third row, the T row altruistic,
Yeah?
since it passes through 2 points in that row?
So it turns out that in every row, there's a way to go through that row where you leave by a diagonal.
Okay.
So I chose a path in this case that I have a horizontal. I think what it would mean is the pivot entry would be the one over here on the right, not the one on the left, so that I leave by a diagonal.
Thanks.
Yes?
I'm not sure if I understand this correct. For the first time you calculate the row U, do you have to calculate everything before it to get U?
Yes. So in order to figure out anything in row I,
Yeah.
every entry in row I depends on some entries in row I minus 1,
Yeah. So,
which depends on some entries in row I minus 2, and so on all the way back to the beginning.
so if you do that, and then you recurse it on the left top part, so you calculate some values that you already been calculating.
No.
Right?
But the trick here is I don't remember all these values all the time.
Yeah.
In the dynamic programming algorithm, I only keep 2 rows. So when I get to row 6, I've forgotten row 3.
Yes.
So I have to recompute row 3
So
later. So later I have to recompute part of row 3.
That's something like you calculate this twice or even multiple times later.
Yes, that's right. So what the recursive algorithm is going to do is I'm going to scan through the entire array, computing values and then forgetting them later, find this pivot, and then in the upper left I'm going to do rescan those values and recompute them and reforget them in order to find a pivot. And then in the upper left corner, I'm going to do rescan and recompute and reforget.
So is that really a better algorithm compared to what?
Well, let's do the analysis and figure it out.
Okay.
Okay?
All right, okay.
So let's first figure out what the running time is. All right, so I've got these 2 parameters, n and m. M is the length of the first string, n is the length of the second. So when I did, to get up to this point in the algorithm where I had the split, I basically scanned the entire array once and did a little bit of overhead work. Then, for some index h, and I don't know what it is, I'm going to recurse on the first m over 2 characters of A and the first h characters of B. And then I'm going to recurse on the last m over 2 characters of A and the last n minus h characters of B. Okay? Now there are some obvious base cases for this recurrence. So if, for example, one of the strings is empty, then I have to write down n insertions. If the other string is empty, I have to write down a bunch of deletions. But the basic recurrence looks like this. Okay. Now, in the notes, there's an induction proof for why this recurrence actually gives you the right values. But I'm going to do something slightly easier, which is I'm just going to throw a recursion tree at it, and you'll hopefully see that it works. So at the very top level, I'm going to do m, n work. At the next level of recurrence, I'm going to do, on the left, m over 2 times h, and on the right, I need to draw a bigger box. And on the right, I'm going to do m over 2 times n minus h work. Okay, and then I'm going to continue recursing my way down, m over 4 times h prime, m over 4 times h minus h prime, and so on. But now if I do the standard thing that I always do with recursion trees, is add up the work at every level. Well, at level 0, I'm obviously doing mn work. How much work am I doing at level 1? M times n over 2. M over 2 times h plus m over 2 times n minus m over 2 times h. The h's cancel, and I'm left with m over 2 times n. And this pattern is going to continue down further levels. If I write out the next level of the recursion tree, the total amount of work that I do on level 2 is going to be mn over 4. So the overall amount of work I do is a descending geometric series, which is dominated by its largest term. It's big O of mn. And if you really want to be cranky about it, the constant is 2. Okay, so this algorithm runs twice as it needs twice as much time as the standard dynamic programming algorithm. Okay, so I'm losing a little bit here. Now let's think about space. What's the space for the algorithm? Well, in order to get to this point, I only needed to keep every row. I only needed to keep a constant number of rows all the way down, and then the suffixes all the way up. So the amount of space that I use in the non-recursive part is order n. And then I'm going to recurse into smaller problems. One is m over 2 times h, n over 2 comma h, and the other is m over 2 times n minus h. Is that right? Is that actually what I'm doing? I'm sort of following along the way I would do things with time. But there's something about this that's a little bit weird. Anyone tell me what it is? I'm sorry? Right. Do I keep that O in there? I don't actually need to keep the entire linear space through the recursive calls. Right? The right way to say this is actually, I'm going to divide my algorithm into two parts. The non-recursive part uses linear space. And then I forget everything except that one column index. Right? And then the non-recursive part uses, well, let's be completely conservative about this. I make a recursive call on a problem with the second argument is size h, and the second call with a recursive argument is size n minus h. And now I claim by induction that the solution to this, of course I've got the arguments backwards here, the solution to this is order n. So by the induction hypothesis, this is equal to order h, and by the induction hypothesis, this is equal order n minus h. When I add those together, I get order n, and the larger of order n is order n. Now, that's not a real induction proof because you have to take the big O's away to do real induction proofs, but substitute whatever constant you like for these big O's, and the whole argument will go through. So the total amount of space I use is going to be dominated by the amount of space I use in the initial non-recursive part of the algorithm, which is 2 rows of the table. So in the end, what I get is the time is big O of nm. In fact, you could really write it as 2mn if you want to be, let's say 2mm writes into some table or other. And then the space is order n, and in fact, I think if you're really being careful about it, you might need 3n cells worth of space. But now what you get out isn't just the added distance, but the actual structure that you wanted to build. Yes?
So do you optimize on the space based on choosing if you go by rows or by columns?
Yes. You can optimize on the space based on whether you go by rows or by columns. So if n is smaller than m, then in fact you want to divide the smaller string, not the bigger string. Right? So you can decide whether to split the table along the middle row or along the middle column based on whether, you want to split along the middle row if rows are shorter, and you want to split along the middle column if columns are shorter. Yes?
When you are doing the recursive flow, I think you should keep one in M1, and you need another two when you are computing M over to the edge and M over to the minus edge. And then you need another four and continue. So I think
I'm sorry, I'm not hearing everything you're saying. Just to say that you're suggesting that there's a piece missing from the algorithm, and I'm not sure I understand what that piece is.
when you are computing the MN, you need a constant memory to save the cell.
Oh, here. Here?
Yeah.
I need, okay, so you're absolutely right. I've ignored the constant amount of memory that I need in order to remember all the basically stacked memory. Right? I've forgotten the stacked memory part of the recursion. Yes, you're right. I've forgotten the stacked memory. So how much stacked memory do I need? How many recursive calls am I going to make? That's really the question. Well, every recursive call is decreasing m. Right? So, and I'm splitting up m. So the recursion tree has, I have m leaves, and I say, okay, I have m over 2 leaves here and m over 2 leaves here. And then, so the recursion tree is only going to have order m nodes. So even if I have to keep the entire recursion tree in memory, which I don't, I would only need order m additional space. In fact, the stack memory is only going to be the depth of that tree, which is log m, which is too small to worry about. Yes?
So you're saying you need both end space to give the row, right?
Yes.
But how would you look at the, say, the recursive column, you look for T row if you've already forgotten?
I recompute it. So in the recursive call on the left, I scan, keeping only 2 rows, the upper left part of this array. So at any given time during that scan, I only need this much space. And then I throw that away, and then in the other recursive call at any given time, I only need this much space. No, the big table has size n squared. N squared is bigger than n. So it would not be cheaper to keep that.
I mean, it's time, since you're not recomputing everything.
Well, okay, but this is the trade-off, right? What I've lost by doing this divide and conquer thing is a factor of 2 in the time. What I've gained is a factor of n in the space. And whether that trade-off is worth it or not is an engineering question. Okay, but if the two strings that you're comparing are each 1 gigabyte long, you really don't want to be using quadratic space. And so losing a factor of 2 in the time is really not such a big deal. Okay. The other way to do this, which is the way that I actually explain in the notes, is to explicitly have another recursive function that says, basically, when I get here, where could I have come from in the middle row? So instead of having a scan downwards to do prefixes and a scan upwards to do suffixes, I really just do one scan all the way down. But when I get to the middle row, I sort of say, hey, this is the middle row. I should start remembering things. And for example, this 4 would remember it came from that 3. This 4 would remember it came from that 3, which remembers it came from that 3. And eventually this 6 would remember not the entire path, but just how the path crossed the middle row. And you get the same kind of divide and conquer analysis. And that way of phrasing the algorithm works even when you don't have the kind of symmetry that you have in the edit distance algorithm. I don't want to go through the details. If you want to see them, they're in the notes. Because I want to do the other thing. Okay? So this is why when we say, describe an algorithm to compute the optimal x, what we're really asking and what we really want is describe an algorithm to compute the cost of the optimal x. Because we know that we can reconstruct the optimal x later, even without losing space, even without, even permitting the space optimization stuff. Yeah.
So where does the O of MN time come from? Is it from scanning through the arrays?
It's from computing these two functions in red. The first one is just do the first half of the edit distance computation, and the second one is do the first half of the edit distance computation on the reversed strings. Okay. So the second thing that I want to point out here, which is a different way of optimizing that actually, I'm now going to save time instead of space, is that there are these special red numbers in the table. These are places where the character in string A matches the character in string B. And if there were none of those, this table would be really, really boring. Right? The way to, the edit distance between a string of length, two strings of length n that don't share any characters is n. I just replace. And the table would reflect that. The table would be really boring. It would just be, there's a 0 in this corner and then 1s, 2s, 3s, 4s, 5s, and so on. So in some sense, all the interesting stuff is happening at these red numbers. These red numbers introduce, if you want to think of it this way, they make the table interesting by changing very slightly the local behavior of this. Think of it as like a wave propagation that goes, when you're it's propagating from the 0 down to the lower right corner. There's a little bump, and it changes the later values that you fill in on the table. And so the observation is that, in fact, if you it's possible to compute the answer by only explicitly considering these particular character pairs. So the running time of my algorithm is not going to, my algorithm is not going to compute the entire table. Instead, all I'm going to do is compute the red numbers and the one down in the bottom left. And in fact, the way that I'm going to do it, I'm going to put a sentinel character at the end of both strings so that the bottom left number is actually red. And then I just say, okay, I'm only going to consider the red numbers, the places where the characters match. Right? Now, doing this for edit distance is a little bit complicated, so I'm going to use a slightly simpler function called longest common subsequence. So longest common subsequence, you should think of this as edit distance where you're not allowed to replace. You can only do insertions or deletions, which means the path that you get through the table is only going to have horizontal and vertical lines. Okay? So the definition of this function, LCS of I comma j, this is the length of the longest common subsequence of the prefix of A that has length I and the prefix of B that has length j. And what a subsequence is you pick out some subset of the characters, but you keep them in the same order. So the subsequence of algorithm might be AGOTM. And a common subsequence is one that appears in both strings as a subsequence. So A, L, R, I, T is a subsequence of algorithm, and it's a subsequence of altruistic. Right? So you can see, in fact, let me just highlight those. A, L, R, I, T. This matches A, L, R, I, T. Okay, so that's a common subsequence of both. And in fact, I believe it turns out it is the longest common subsequence of both. And if I add this sentinel character at the end, now I have a longest common subsequence of length 6. Hey, look, it's 6. And you get this recurrence, which looks very much like the edit distance recurrence. I look at the initial characters of the two strings. If they're the same, then I say, yes, this is part of the longest common subsequence. If they're different, then I either throw away the first character of A or throw away the first character of B, and I recurse. The pattern of recurrence is almost the same as edit distance. I scan the array in row major order. The difference is that when I look at a particular number, I'm only going to look at the neighbors north and west, not the neighbor northwest. And I'm always going to take, the minimum of those two and add 1. Or if it's a red number, if it's a special number, I'm always going to look diagonally and add 1. Actually, longest. I'm going to take the larger of these two bits. Okay, sorry. So in this particular case, if none of the characters were equal, if I had two strings that had completely disjoint things, this entire table would be full of zeros. Because I'd always be exercising the third case in this recurrence, where I look above me and by the induction hypothesis I have a 0, and to the left of me where in the induction hypothesis I have a 0. Okay. So the only thing that's actually happening here is when I see two characters that match, this is an opportunity to add 1. Right? This is the only place in the entire recurrence where I can do anything other than have a 0. Okay, so the standard algorithm scans through this array in row major order in nm time. I can compute the bottom number by only keeping a linear amount of space. I can do the Hirschberg divide and conquer trick to actually get the longest common subsequence out later, still using only a linear amount of space. That's great, but in fact, all of the interesting behavior in this table is here. In these red numbers where things actually match. And the pattern in these numbers is the following. If I consider any square that isn't one of these red numbers, the number that goes there, remember, all the values sort of propagate from above and to the left. I look at everything that is either above or to the left, and I find the largest number, and I put it there. All right, so R versus T, that should be a 3, and R versus T, sure enough, that's a 3. Okay. For the red numbers, what I'm going to do is look strictly above and to the left, because the red numbers in the table I copy from above left, and then all that value comes from everything. This number is the same as this one here. So I look in this quadrant above and to the left. I find the largest number, and I add 1 to it. Okay. So the way that I want to think about solving this problem is step 1, find all matching pairs. Right? So these are interesting positions in the table. And then consider these matches in the right order. And then the value at any match is going to be 1 plus the maximum value that is above and to the left. Okay? So if I want to compute, there's an interesting position in the table here. I'm going to look strictly above and strictly to the left. And out of all these interesting values that show up in there, I find the largest one and I add 1. Another way of drawing this picture, let me erase this, is to think about sort of layers. There's a 0 that just corresponds to the sentinel at the beginning. So I've got these weird layers where, because of the rules that I'm playing with, everything in this layer is going to be a 5, everything in this layer is going to be a 4, everything in that layer is going to be a 3, and so on. I can sort of summarize the table by building these layers of what look like staircases in a more interesting example. And so all I'm asking when I pick out a new interesting thing is, how many staircases am I under? How many things have I already built over my head that separate me from that 0? All right. So what does this look like in terms of actually writing a recurrence? So I think the picture is clearer, but some people like to actually see things that look like code. What this says is that if I want to figure out a particular entry in the table, if I have a match, then I looked strictly above and strictly to the left. I find the largest value of a match in that quadrant, and I add 1. If I'm in a boring place in the table, I look loosely to the left and loosely to the right, and for a place where I do have a match, and I take the largest of those values. Now, if I'm only going to be executing this recurrence on the interesting values, I can just ignore this last line entirely. And now the way that I want to do this is, well, first I need to find all the matching pairs. I need to find all the places in the table where I might write a red number. So how do I do that? How do I find all the places where a red number would go? I'm sorry? I'm sorry, just...
Do a for loop?
Yeah. Well, I can do 2 for loops, but the whole point here is to save time. So what I don't want to do is say for each character in A, scan B, because now I've already used NM time, and I might as well just use the standard algorithm. Okay, one way is I could use a hash table. I could say take each of the letters in A, hash it. Then for each letter in B, look it up in the hash table. Another way I could do it is by sorting. Sort string A in alphabetical order, sort string B in alphabetical order, but remember where the characters came from, and then essentially do a merge. Right? So the specific details are in the notes, but essentially in time, linear in the sum of the lengths, not the product of the lengths, I can find all these interesting positions. Okay? So finding all these matches I can do in roughly m plus n time. I need logs if I do sorting. I need to say expected if I do hashing. But morally, this is not going to be the bottleneck anyway. Yes?
So if all the characters match each other, won't you have all the numbers be right?
Ah, plus the number of matches. Okay, so I need a term that's linear in the number of things that I output. So if in fact string A consists of all x's and string B consists of all x's, then the output size is going to be mn. Right? But there's pseudocode in the notes that shows how to do this. Once I have the string sorted, if I find a block of f's and another block of f's, at this point I can write down all the matching places with f's in just 2 for loops. So if I have few matches, it's going to run in linear time, just skipping through. If I have lots of matches, I'm going to be spending most of my time writing down the answer. So I need this plus k term, where k is the number of matching pairs. Okay. And now, from now on, everything is going to be analyzed in terms of k. Right, so I have a list of pairs of indices. So there's a match at 1, 1, there's a match at 2, 2, there's a match at 4, 4, there's a match at 3, 6, and so on. And remember, the rule is to figure out what the value is at a particular interesting number. I look strictly above and to the left, find the largest number up there, and add 1 to it. So, what order do I need to consider these red numbers? I need to make sure that when I get to this red number, I've already seen all the red numbers above and to the left. So what order should I use? Yeah. Left to right, top down, standard row major order. Right. So the order where that I want to evaluate these things is this order, just like the standard dynamic programming thing. Now, how do I get that order? I've got these pairs. That up there is a 0, 0, 1, 1, 2, 2, 4, 4, 3, 6, 5, 6, or 6, 5, 8, 5, 7, 6. Right? I've got these pairs that somehow I need to order consistently with these green arrows. How do I do that? Sort. I sort the pairs first. I sort them by their column, by what row they're in, and I break ties by what column they're in. So I can do this in k log k time. And then for each one of these, I just scan through all of the earlier ones. Now, some of the ones that are earlier in order are actually to the right, but I can figure that out in constant time. I scan through all the earlier ones and take 1 plus the largest one that's actually relevant. Okay? So, find all the matches. I know how to do that. Roughly, I'm going to add a sentinel at the end because it simplifies the bookkeeping. I do the sorting lexicographically, which means for each pair, I compare the first indices, and if they're equal, I compare the second indices. Then I scan this list of matches in order. I pull out the next match, and I, for the moment, have a placeholder value of 1. And then for all of the earlier matches in lexicographic order, I pull out those indices, and if the indices have the right condition, then I apply them in. And so in the end, this algorithm is going to run in time. There's m plus n plus k pre-processing, and then how long does that for loop take? How long do I need to do this? Oh wait, I needed k log k to sort. And how long does that chunk of code with the for loop take?
K squared.
K squared. So this actually is faster if k is sufficiently small. Right? Let me simplify things by saying m and n are equal. right? The standard algorithm runs in n squared time. Provided the number of matches is less than n, this algorithm will actually be faster than the standard algorithm. Now, in the worst case, k is n squared, and this is horrible. Nevertheless, this is the first algorithm that was discovered for longest common subsequences.
Oh.
It wasn't discovered in exactly this form. There was a bit more brute forcing to it. There wasn't like pull out the matches. It was more like discover the matches on the fly. But morally, this is an algorithm due to Nienelman and Wunsch in, I don't know, I think it was 73. I may be off by 1 or 2 dates. And the important thing is that the running time was quadratic in the number of matches, which in the worst case is really, really awful. But we can do better. Okay, we can do better than this. This part of the algorithm can be optimized down to just k log k. Which means as long as the number of matches is substantially less than the whole table, it's faster to do it this way. Okay. Now, how does that faster algorithm work? I think maybe what I should do is get a pristine copy of this thing and paste it here. Okay. I said pristine. Okay. So I want you for the moment to ignore the fact that these are numbers. And I want you to just think of them as positions. Now, I'm going to build a data structure. Hey, a data structure. We haven't used it you've all taken 225. You remember data structures. I'm going to build a data structure that allows me to answer the following question quickly. Given an interesting position, right, so the data structure is going to store all of the interesting positions. And I'm going to say, given an interesting position, find the largest value among all the interesting positions above and to the left. Okay. Well, this turns out to not be exactly what I want. Because I've got sort of 2 dimensions to worry about. If I only had 1 dimension to worry about, then you might think I can adjust some kind of binary search tree-ish thing. Binary search trees are a nice way of encoding everything to the left, right? But everything to the left and above, that's a little bit more complicated. So maybe I can adjust this to just be everything to the left. And that turns out to actually be okay because when I'm considering this 4, I haven't figured out these other later values yet. So in fact, the only things that are, when I figure out the value, I'm going to throw it into the data structure, which means everything that's in the data structure is already above the 4. If you're getting lost, it's okay. Let it wash over you. It's not going to be in the homeworks. Not going to be in the exam. I want you to get the feeling that, hey, there's some clever stuff that one can do to speed this up using binary trees. The details are not what I want you to remember. Just the sense of what's going on. Okay. So I'm going to be scanning these interesting things from top down. Whenever I figure out a new value, I'm going to throw it into a data structure. And later when I get another value and say, out of all the things I've already computed, what's the biggest value that I've seen to the left? Yes?
That's a little bit confusing at the beginning. Numbers
Okay.
Supposed to match what matches the letters that are matching.
Right. These positions correspond to where...
Yeah, they're all shifted.
They're all shifted. Oh, crap. Okay, all these numbers are supposed to be over 1. Sorry. All right, so all these numbers are that's a vertical line. Sorry. I will go back into the notes and fix that. I apologize. Okay. Let's just pretend for the moment. Let me see if I can fix this. Okay. All right. So what should these letters be? That should be an I. That should be an I. Come on. Oh, I have to. The O is also wrong? Okay, forget it. I'm going to try to fix this on the fly. The letters are wrong, so in the interest of not distracting people, let's just, not pay attention to the specific values here. Trust me when I say there's a match at each of these red positions. Okay, so I want to find, out of all the values I've already computed, each of those values has a position, and I just need the horizontal position. Out of this list of numbers, 0, 1, 2, 3, 3, that 3 is too far to the right, so I want to ignore it. I want to pick out, among all these things, the one with the largest value. So the way I'm going to do this is I'm going to keep a binary tree, okay, that is indexed by position. Right, so the search key that I'm going to use in the binary tree is the X position. In this case, this is index, 6 in the horizontal string. So I'm going to use 6 to look things up in the binary tree. And I'm going to use the standard binary tree search algorithm to find it. But what I'm going to store in each of these nodes is the largest value that shows up anywhere in the subtree. So when my search path goes to the right, I can look over here and say, oh, I know everything in this subtree is to the left. Right here is the largest value that shows up into the left. That might be the largest value, the value that I want. The important thing is that I can answer this query in log k time. Essentially, I'm just doing a search in a binary tree. And then I can insert this new value into the data structure in log k time, because I'm just inserting something into a binary search tree. Oh wait, in order to get logs, I need a balanced binary search tree. So pick your favorite balanced binary search tree. Red, black, AVL, B tree, skip list, splay tree, whatever. Whatever you've seen before, balanced binary search tree is what you would write down. You can do this query in log k time, and you can do the insertion in log k time, which means you can replace this inner for loop here with a data structure call that runs in log k time. And that allows you to replace this k squared with k log k. And that is the algorithm that people actually use in practice when there are lots of different characters, when the number of matches is relatively small. I know it went fast, but fortunately you don't have to remember it. All right. I'm happy to answer questions, but otherwise we're done. Thank you.
Yeah.
Yes.
Do you remember the